You might remember that this equation here is the most important differential equation in the world, and it has a solution that is an exponential, right? It's c e to the rt. And what we're going to do now is think, instead of about first-order equations, about second-order equations that have constant coefficients. So this is kind of the second-order equivalent of or the second-order extension, maybe, of the most important differential equation in the world. It's this one here: y double prime plus py prime plus qy equals 0, where p and q are just some real constants. And perhaps at another point in this course, you'll learn another way to solve this equation that does not involve guessing and just involves using linear algebra. But for now, the way I want you to think of solving this is by making a guess, or sometimes we use the awesome word Ansatz. It's a German word, basically meaning an educated guess. And the thing we're going to guess is an exponential, something of the form y equals e to the lambda t, where lambda is a number that we don't know what it is yet. And we take it and we substitute it into this equation, and from differentiating twice, first term gives us lambda squared e to the lambda t, second term gives us p lambda e to the lambda t from differentiating once, and then we have q e to the lambda t. And we could think of dividing through by all the exponential terms, and if we do that, we're left with this equation: lambda squared plus p lambda plus q equals 0. That's just an algebraic equation. It's called the characteristic equation. And of course you can solve it using the quadratic formula, and you get this solution here. And I want to kind of show you how this works, doing some concrete examples, but they're concrete examples divided up into the different basic cases that you might encounter. So case 1 is the case where there are distinct real roots, two distinct values of lambda. So the examples y double prime minus y prime minus 6y equals 0. You'll learn to just read off directly that the characteristic equation coming from these coefficients is lambda squared minus lambda minus 6. That's mirroring these coefficients here. Lambda squared minus lambda minus 6 equals 0. That's factorable, and you find that the roots are lambda equals -2 and 3. Two choices for lambda means there are two possible exponential solutions, right? There's e to the -2t and e to the 3t. Now we'd like to write down the general solution. Since it's a second-order equation, and we have two linearly independent solutions here, they form a fundamental set. So to write down the general solution, we just take a linear combination, and we have c1 e to the -2t plus c2 e to the 3t. Alright, for the next example, let's assume that we have purely imaginary roots. So an example of this is y double prime plus 9y equals 0. The characteristic equation is lambda squared plus 9 equals 0, and the roots are lambda equals plus or minus 3i. So a fundamental set of solutions are the exponentials e to the 3it and e to the -3it. And so the general solution is c1 e to the 3it plus c2 e to the -3it for y. Since you can think of the parts of the fundamental solutions as kind of like vectors in a basis, you can think about changing bases. And since we had an equation that started out with real quantities up here, sometimes it's desirable to write your solution in terms of real quantities. And so another basis is cosine 3t and sine 3t, and we can write the general solution as c3 cos 3t and c4 sine 3t. If you don't believe me that these are really just the same solution masquerading in a different form, you can take this first way of writing things here and apply Euler's formula. So this term here becomes c1 cos 3t plus I c1 sine 3t, and by Euler's formula, this term here becomes c2 cos 3t minus I c2 sine 3t. Alright, so then what we're going to do is just organize terms by cosine and sine. If I gather the cosines together, I get c1 plus c2 cos 3t, and if I gather the sines together, I get I c1 minus I c2 sine 3t. I give this combination of arbitrary constants a new name, I give this combination of arbitrary constants a new name, and that gives us this solution here, c3 cos 3t plus c4 sine 3t. Okay, don't get confused here. It's not that like you've somehow gone from having a complex solution to having a real solution. The solution is always real because the original equation is real, right? So even though this one here looks complex to you, what you haven't used is a real initial condition. And if you used a real initial condition, you would find that C1 and C2 turned out to be complex conjugates of each other, so that the overall value of y was real. Okay, and if you reorganize the information like we did using Euler's formula, you can write the solution this way in terms of cosine and sines with real coefficients. All right, here's another case. This is the case of complex roots. So an example is y double prime minus 4y prime plus 29y equals 0. So the characteristic equation is lambda squared minus 4 lambda plus 29 equals 0. And using the quadratic formula, if we simplify a little bit, we find that lambda is 2 plus or minus 5i. So here's the fundamental set of solutions. And again, we just take exponentials to form our general solution. So that's c1 e to the 2 plus 5i t plus c2 e to the 2 minus 5i t. Both terms have a factor of e to the 2t, so we factor that out in front, and we're left with this quantity in the brackets, c1 e to the 5it plus c2 e to the minus 5it, and hopefully above, in the previous case, I convinced you that another way to write this is as a combination of cosines and sines. So we can write the solution neatly in terms of real quantities as e to the 2t c3 cos 5t plus c4 sine 5t. So that's a solution that's growing exponentially in time and has some oscillation to it as well. All right. The last case is the case of a repeated real root. So the example here is y double prime minus 6y prime plus 9y equals 0. Characteristic equation is lambda squared minus 6 lambda plus 9 equals 0. That can be factored as lambda minus 3 squared equals 0, so lambda equals 3 is a repeated root. So naively, we know that one solution is, c1 e to the 3t, right? However, this is a second-order solution, a second-order differential equation. So to form a fundamental set of solutions, we need two linearly independent solutions. We only got one from solving the characteristic equation. So again, we're going to make a guess. And what we're going to do is show that the guess produces a solution. It will be evident that the solution is linearly independent from the one we've written down here. And since there's two things that are solutions and they're linearly independent, we will have a fundamental set. Okay, so the thing we're going to guess is that there's a second linearly independent solution equal to the first one, e to the 3t, times some unknown function of t. I'm just going to call it v of t. We don't know what it is. The way we're going to find out what it is by taking this guess, plugging it into the equation, and seeing what has to be true about v in order for this whole thing to be a solution. So, since when we plug in, we're going to need derivatives of y, I'm going to pre-compute those derivatives. So I take my y2 here, and I calculate the derivative, y2 prime, using the product rule, is v prime e to the 3t plus 3v e to the 3t. And I can factor out the exponential and just write it as e to the 3t times v prime plus 3v. To calculate the second derivative here, I'll just differentiate the line above, and I have to use the product rule a couple of times, but I get v double prime e to the 3t plus 3v prime e to the 3t plus 3v prime e to the 3t coming from the second term up here, plus 9v e to the 3t. And if I factor out the e to the 3t's and combine this term with this term, then we find e to the 3t times v double prime plus 6v prime plus 9v. Now I'm going to take this information here in our original guess for y2 and substitute it into the original differential equation way back up here. All right? So y double prime becomes this business. Then I have minus 6y prime. Sorry, that's my dog in the background. Minus 6y prime becomes this business. And then we have plus 9y, which becomes this business. And you can, of course, divide through by the factors of e to the 3t. And if you do that and expand things, what we have left is here v double prime plus 6v prime plus 9v minus 6v prime minus 18v plus 9v equals 0. But there's a lot of cancellation. These v primes cancel, and 9v plus 9v minus 18v cancels, and what we find is just v double prime equals 0. You can solve that by direct integration, right? If something has a 0 second derivative, that function, if a function has a second derivative that's the 0 function, that original function has to be a line, right? So that's what we have here. V equals c2t plus c3. So now our final solution is the original one, c1 e to the 3t, the one we got from solving the characteristic equation, plus the one we got from our guess. So that's c2t plus c3 e to the 3t. There's two terms that just are e to the 3t, and so we can group those together here, and then we have our t e to the 3t term, and we'll give a new name to the arbitrary constant c1 plus c3. We'll call it c4. So our final general solution is an arbitrary constant times e to the 3t plus an arbitrary constant times t e to the 3t. And I don't want to give you too many hard and fast rules, but this is generally what's going to happen when you have a repeated root, is that you're going to have the original solution that you found multiplied by one higher power of t here. All right, so overall, what have we done in this lesson? We've used the method of the characteristic equation to solve some second-order linear constant coefficient differential equations. I'm just going to conclude by saying that this exact same method works if the equation's higher order. There's nothing special about second order here. You could do it for third-order constant coefficient or fourth order or so on up. And all that really changes is that your characteristic equation ends up being a polynomial of higher order. All right. Thanks for listening.